Hello, my name is Adib Ahmadzadegan. I'm from the Mechanical Engineering Department at Purdue University, and today I'm going to present our work on uncertainty estimation for ensemble particle image velocimetry. Uncertainty is the interval around a measurement that with some confidence it's supposed to contain the true value. The uncertainty of PIV measurement depends on three main categories. One is the image quality, and by that I mean the particle seeding density, the image noise, the illumination, and so on. The second one is the processing algorithms, whether you're using instantaneous PIV algorithms or ensemble PIV, whether you're using standard cross correlation or phase correlation, if you're using discrete window offset or image deformation, and so on. And the third one is the flow field of interest itself. For example, if you have a uniform flow where all the particles are moving with the exact same displacement, then the uncertainty of your velocity estimation for that flow field is a lot different than the uncertainty in velocity measurement of a flow field that the particles' displacement are contaminated with some Brownian motion or randomness. Now, ensemble PIV is developed to improve the signal-to-noise ratio in the cross-correlation plane. If you look at the instantaneous correlation planes in the figure I'm showing here, you can see that the signal-to-noise ratio is not sufficient to perform a reliable velocity measurement. But when you take these instantaneous correlation planes and average them, then you get a cross-correlation plane with an improved signal-to-noise ratio. Now, despite the utility of ensemble PIV and the wide usage of such algorithms, there is no uncertainty quantification algorithm developed for ensemble PIV. The existing methods are developed for instantaneous velocity measurements and do not account for the improved SNR in ensemble PIV. Among the existing instantaneous uncertainty quantification algorithms, the method called moment of correlation, or MC, could be adapted for ensemble PIV. This method works by finding the width of the PDF and normalizing that by the effective number of pixels that contributed to that PDF. To modify MC to work for ensemble PIV, we made two main modifications. One is that we use ensemble correlation plane instead of the instantaneous correlation plane to find the width of the PDF. And secondly, we updated the normalization factor to account for the number of bright pixels in all the images that goes into the image ensemble. However, there are two major limitations to the moment of correlation approach. One is that it assumes the intensity shape of the particles follows a Gaussian profile. And secondly, the PDF of the displacement follows a Gaussian distribution. With these two assumptions, MC can find the width of the PDF. But these assumptions are not always met in experimental images. To address the limitations of ensemble MC, we developed the method called moment of probability of displacement, or MPD. In this algorithm, we utilize a method called image-based probability estimation of displacement, or iPED, which is a direct approach to find the PDF using ensemble correlations without making any assumptions about the shape of the particle or the shape of the PDF. In short, this approach works by deconvolving the ensemble cross-correlation plane by the ensemble autocorrelation plane in the spectral domain. Now, from the PDF of displacement found from iPED, with some pre-processing steps, we can calculate the second moment of the PDF, or also known as the width of the PDF, in a discrete manner. We then scale the width of the PDF that we found by the effective number of particles that contributed to the correlation plane, and then report the uncertainty in the velocity measurement. The PDF plane that we get from iPED is rather noisy. And since we are going to calculate the standard deviation of the PDF in a discrete manner using the estimated PDF plane, we pre-process the PDF plane to remove the noise floor from the PDF. To avoid modifying the plane while eliminating the noise, we decided to use a thresholding approach. The thresholding criteria comes from the root mean squared, or the RMS, of all the PDF values in the PDF plane. And if we use this RMS value, you can see that we can remove most of the noise in the PDF and end up with a much cleaner PDF. Now we use this cleaned up PDF without applying any model or assuming any shape for this PDF. we directly calculate the width of this PDF by discretely calculating the second moment of this PDF. So once we find the width of the PDF, the next step is to normalize it so that we can report the uncertainty in velocity measurement. To be consistent with the definition of standard error, we define our normalization factor as the square root of the number of observations that go into our measurement. The number of observations come from the mutual information between frames and the number of image ensembles that we used. And finally, we would get the uncertainty in the PIV measurement. Now, as a reminder, the normalization factor that goes into the MC algorithm accounts for the number of pixels that go into our correlation plane. And that's why you can see it also includes the area of the pixels in its normalization factor. Now we have two methods for reporting uncertainty in Ensemble PIV, MPD and MC. To do a performance assessment on these and compare them against the error, we designed a Monte Carlo analysis where we used synthetic data sets and varied parameters that are known to affect the error in PIV. In our study, we looked at the effect of particle displacement, particle size, concentration, the diffusion coefficient, which accounts for randomness in the images, the background noise, and the number of image ensembles. The baseline parameters are kept constant while other parameters were varied in our images. For the baseline, we have a uniform flow with no shear, and the particle size, the concentration, and the rest of the parameters are shown here. So once we generated our synthetic data sets, we performed the PIV processing to report error in a measurement and be able to compare that to the estimated uncertainties. We were using a multi-grid image ensemble approach with standard cross-correlation and 3-point Gaussian fit for the peak location. We are using 2 passes with validation and the final pass without a validation. And the window size is 64 by 64, and we have a 50% window overlap. Here we show our results of the Monte Carlo analysis. Now, it has been established that a reliable uncertainty quantification algorithm predicts uncertainties that their RMS matches with the RMS of the error. So for comparison, here in these plots, for all those different PIV error sources that we studied, we report the RMS of the error in black and the RMS of uncertainty estimations using Ensemble MC in blue and using MPD in red. Now you can see that the red line matches with the black line in most of the cases that we studied, and it consistently outperforms the MC approach. Next, we performed an experiment to demonstrate our algorithm's performance. In this case, we performed an experiment with a flow in a microchannel. Since we set all the parameters and we know all the details about the microchannel size, the flow rate, and so on, we can report an error in the measurement. We also performed uncertainty quantification using MC and MPD. Here I'm showing error distribution in black and uncertainty distribution from MC in blue and MPD in red. I'm also showing the RMS of each of these methods, so you could see the RMS of the error, which is the black horizontal line, matches very well with the RMS of the uncertainty that comes from MPD, horizontal red line, while MC, which is the horizontal blue line, underestimate the uncertainty. To conclude, we presented MPD as a novel approach for estimating uncertainty in Ensemble PIV. We showed that MPD has a good sensitivity to all different PIV elemental error sources, and it outperforms the Ensemble MC. We also demonstrated its performance on an experimental dataset. MPD is a reliable tool for semi-steady state time-resolved datasets such as micro PIV experiments. Thank you.